Namaskar. Welcome to Prakash on Basics. I'm Prakash Zog. As you'll notice, the symbol this time is different. The reason is I'll be using this symbol whenever I talk on topics related to science. As well informed, knowledgeable, civilized people, we need to know the working, reasoning, the logic behind many of the things that are around us. And many a times they are based on science. Uh, Many of these things we might have learned when we are in school, but that's long time ago, and our logic and understanding has changed. So we need to rethink about all these and know them perfectly. I plan to cover the basics of many scientific aspects around us, from Big Bang to the working of the human body. Uh, all that every curious, intelligent mind of a human being must know. I'll keep things simple as far as possible. Uh, I'll deal with physics, I'll deal with chemistry, I'll deal with biology, deal with space, mechanics, machines, music, and so many things. But I'll keep them down to a bare minimum of 15 to 20 minutes, and I'll avoid as much of maths as possible and stick to discussions. A great author once said, what does a man need to survive? Food, clothing, and shelter. That's all. A great sentence. It was believed by a lot of people, translated in so many languages. Sadly, scientifically, that sentence is not really true. So, what do we need? If you think carefully, you might come up with oxygen, water, food. But what's the use of all these? All these three facilitate a process which involves the release of energy. At the core of our existence, not only us, but of all life, is energy. So, what is this energy? Let's try and understand it today. The capacity to do work is defined as energy. That's a simple definition that is there given in scientific books. If I need to do anything or get anything done, what I need is energy in some form or the other. To talk, to walk, to throw a stone, to build a building, to make something, even to breathe, even to sleep. Everywhere, what I need is energy. The instant it stops, my existence ends. This energy that we know of has many different forms: heat energy, light energy, sound energy, electrical energy, mechanical energy, nuclear energy, magnetic energy, chemical energy, and so many different forms. And sometimes we know these other names also. We hear of kinetic energy and potential energy and wind energy and solar energy and geothermal energy, atomic energy, elastic energy, so many of them. Surprisingly, many of them are a combination of the first few that I mentioned in the beginning. They are just different forms of the initial ones. They could be a combination of one, two, or more of them. For example, wind energy is nothing but mechanical energy. Geothermal energy is heat energy associated with Earth. Um, and kinetic energy and potential energy are both parts of the mechanical energy that we generally talk of. Um, this potential energy itself could be either due to gravitation, or it could be due to magnetism, or it could be due to electrostatic forces. We'll go into details of that, all that, and try to break up all that later on. This all this is more or less like the multitude of gods that we have in India. Finally, all of them are the same. It's the same representation of the final entity. Its manifestations are different, that's all. Its effects are very specific to that particular form. The way of producing a particular energy could be different. The rules that it has could be different. The laws it follows could be interpreted in different ways. The applications it has naturally would be different. So its form itself could be different. But finally, they're all just energy in the end. In due course of time, I'll discuss each and every one of them independently because they are far more important for us in life. I'll discuss them and their uses also. Let's look into the basic types of energies first. Any form of movement or an attempt towards movement results in mechanical energy. It also requires energy which can be converted in the form of mechanical energy. It is usually the sum of the potential energy, that is energy due to position, and in most cases we talk of this position in terms of gravitational positions. And the second part deals with kinetic energy, that is energy associated with movement. Any object in motion and which has mass possesses kinetic energy. We've talked of this in our schools sometime as potential as kinetic energy being half mv squared and so forth. Let's keep that aside. Um, if an object has mass, it has kinetic energy. If it has speed or velocity, it has kinetic energy. But it's not all that straight. If the mass doubles, the kinetic energy doubles. If the speed or the velocity doubles, the kinetic energy increases four times. And if both of them change, naturally, there will be correspondingly that much amount of more energy in the form of kinetic energy that a body would possess. Think of, to understand this, let's think of a simple thing like a bullet, for example. I take a bullet, just toss it at something, there's no effect. But the same bullet, when I fire it through a gun, it acquires an extremely high velocities in the ray, which is typically known as muzzle velocity, 800 to 1000 meters per second. And it is this that gives the bullet that great amount of energy by which it can penetrate through a human body or through so many other things. And if the speed is small, when I just take a bullet and drop it on my hand, nothing happens. So if the speed is small, does it really mean that the kinetic energy is less? No, it is possible that the mass could be very heavy. For example, if there is a road roller moving at just 4 or 5 centimeters per second, its velocity could be less, but its mass is very big. So its kinetic energy could be extremely high. So both the factors put together decide on energy possessed by a body due to its motion, and this is kinetic energy. So any object in motion having mass possesses kinetic energy. Now, the second half of mechanical energy, which is talked of as potential energy. As I said, most of the time when we talk of mechanical energy, we refer to the gravitational aspect of potential energy. Anything that is raised up gains what is known as potential energy. The higher you raise it, the more energy it would gain. So if I climb to the first floor, I have a certain amount of potential energy. If I go to twice that height, I will have twice that amount of potential energy. On the other hand, if I have an object of mass 1 kg lifted and instead of that 2 kg lifted through the same height, 2 kg would have double the amount of potential energy. So it depends upon what is the amount of mass, and it also depends upon the amount of height that it gains with respect to the ground level. And that is potential energy. For all general purposes, at this stage in the beginning, potential energy plus kinetic energy gives you the total energy of the body in its mechanical form. Please realize that elastic forces and springs that are compressed because of their position, also store amount of mechanical energy. That also is a part and parcel of the same thing that I've been talking of. And this potential energies could be due to electrostatics and magnetism too. We'll come to that later. Now, there is another major form of energy that we know of, which is heat energy. Heat energy, whenever we talk of heat energy, we usually talk of temperature. But that's the effect that helps us to measure heat energy. Actually, the energy associated with heat is associated with the vibrations of the molecules or atoms within an object. If they vibrate more, the temperature is higher, they possess more amount of heat energy. And the vibrations could be in straight lines like this or twisting around and so many other forms. We'll come to that when we talk of heat energy. Then there is electrical energy. And there are, as you know, charged particles. And the most important one of them is the electron. And there are things like ions, which are also charged. And when there is a term that we often hear of, that is the potential or the potential difference, which is voltage, which we know at home to be 220 volts. That voltage causes these charged particles to move, which results into current. And this combination of voltage and current and time put together gives us the amount of electrical energy that is possessed by that particular current voltage flowing for a certain amount of time. And what about light energy? There are certain types of waves. They are known as electromagnetic waves. When electrons go from lower levels to higher levels and come back, they emit this radiation. A certain part of this radiation is the one that we talk of as light energy. It's a very big spectrum, like a big book. Out of it, the part that is associated with light is a very small part, and that contains a certain amount of energy. That energy obviously is light energy, and it depends upon the frequency or the number of vibrations of this particular wave that is being produced. And suppose these vibrations are mechanical in nature, in an elastic medium, then that particular wave results into what we know of another form of energy, which is the sound energy, which is usually produced in different objects or most typically, as we know of, in air. And it is produced by objects like my throat and other areas which are associated with elastic movements. So that is sound energy. And when atoms exchange their outermost electrons and combine with each other to form molecules and compounds and so many other things, they start storing a certain amount of energy that we know of as the chemical energy. When they break down, this energy is released. So all that part is commonly talked of as chemical energy associated with exchange of electrons or ions for that matter. And when inside the atom there is something known as the nucleus, if that starts combining with other nuclei or if it breaks down into other nuclei, what you get is the nuclear energy. Some people tend to call it atomic energy still. And in fact, our government used to talk of the Atomic Energy Commission and so forth. In true sense, it is now typically referred to as nuclear energy because it is associated with the nucleus of any particular atom. So there are, as you can see, so many different forms of energies that I've been talking of. One of the most important principles associated with energy is the first thing that we must know of, and that is known as the principle of conservation of energy. Energy cannot be created, energy cannot be destroyed, but it can be converted from one form into another. Man has used this particular principle directly or indirectly, even without knowing it, for his own advantage right from early days. when mechanical movement like hitting stones together produced sparks and then produced fire, which was used to burn wood or coal, which was chemical energy stored in them. The maximum utilization, sensible utilization of this particular principle has led into the development of humans in general. How do we understand this principle? Let's try and take a very simple example. Uh, let's say I'm communicating to you through my computer. So what you're seeing is a picture, more like a TV screen or something of this sort. Okay, let's talk of the TV itself, which all of us know. Um, what does the TV work on? Electricity. Where does that means electrical energy? Where does the electrical energy come from? It comes from some hydel plant or some thermal plant. So it is using either potential energy of water falling through, resulting into turning of turbines, which produces electricity, or it uses certain chemicals, or it uses nuclear energy to produce and rotate the turbines to produce the electricity. So again, it is linked either to mechanical form or it is related to chemical form. If it comes through water that falls, where does the water come from? It comes from clouds. And where does the water come into the clouds from? From the sun. So I am using solar energy to heat water that goes into steam, that condenses, falls as rain, results into the turning of turbines and so forth. And where does the sun get its energy from? And that comes from the reaction within the sun in terms of hydrogen converting itself into helium, which is a nuclear reaction. But where did the hydrogen and helium come from? They came from the Big Bang, the first big energy source, which converted a lot of matter into all these gases and other stuff that we talk of. So, and let's not stop at this point. What does the TV produce? It produces happiness, fine, and sorrow, that's aside. But you see a picture, it means there is light and there is sound produced. And the TV gets hot occasionally, that means heat energy is being produced. And without a magnetic field inside the TV is not going to work, which implies that in all these cases, all the energies that we talked of so long have been linked up. And think of the sun itself, the solar energy. What is that finally? It is a chemical energy, or rather nuclear energy, that is being converted into heat and light, which finally reaches us on Earth. And that's our major source of energy on Earth all along for so many billion years. So you will find that this principle of conservation of energy is one of the most important principles that man has used very effectively to utilize energy for his own gain, even for his own existence. Because the solar energy results into photosynthesis. Photos is light, synthesis is putting together. We'll go into details sometime later, but that's how our food is produced. And it is this food that breaks down with the help of oxygen and water that I talked of some time back to release the amount of energy that drives all our cells, including our brain. So everything finally boils down to the interrelation between a variety of energies that we've been talking of. All this worked fine, uh, worked for thousands of years, and development scientifically was up to last 200, 300 years. But around 1905, there was a big change. Einstein proposed an equation, E equal to mc squared, and it changed the concept associated with energy to some extent, because it was here that people realized that energy is not undestructible. It can be converted into another form. It can be converted into mass, or mass can be converted into energy. And the equation which I just talked of, E equal to mc squared, that, by the way, is not the equation for which he got his Nobel Prize. He got his Nobel Prize for photoelectric effect. But this equation, E equal to mc squared, is probably more applicable to things around us. The equation is not very simple. M is the mass of an object that is being converted. we talk of it in terms of kilograms, and c is the velocity of light, which is 3 lakh kilometers per second, or 3 into 10 raised to 8. That means 3 followed by 8 zeros. So many meters per second. So when I square it, it becomes 9 followed by 16 zeros. So when 1 kilogram of matter is converted completely into energy, we get a very large amount of energy. We don't even seem to realize the numbers involved. Let me just give you a slight idea. We all use electricity at home, and we know the kilowatt hour or the 1 unit of electricity that we get at home. If I convert 1 kilogram of matter into complete energy, I'll get 25 followed by 11 zeros. So many units of electricity. It's a very complicated number. Let me make it more easy. It's like we normally consume around 500, 600. Let's say 600 units per month. So a family consumes, let's say, simple family converts uses 600 units per month. So in um, a year, 7,200 units. Now, if I have 1 kg of matter converted into energy, I will be able to run 1,000 such families consuming 600 units per month for 3,400 or close to about 700, so many years. That's 1 kilogram of energy. And we have our nuclear plants that work. They don't consume so much, or they don't produce so much amount of energy. The numbers are different. We'll talk of them sometime. But this is only to give you an idea as to how big all these numbers really are. Just to give you a hint, look at the amount of matter that we have around us. Earth, sun, stars, galaxies, planets, whole universe, all that matter has come from some energy at Big Bang that converted itself into matter at that instant. You can just about imagine how big this amount of energy would be. So that is the E equal to mc squared relation that talks of energy as one of the basic aspects. This is science. So everything has to be measured. For any sort of a measurement, you need units. I just talked of a few of them. Uh, for different forms of energies, it is quite obvious that these were not discovered at simultaneously. Electricity is much later, heat is much earlier. So units and were for heat were much earlier. Also, the people who really talked of this scientifically were from different communities. The British had their own ideas, the French had their own ideas, the Germans had their own concepts. And so naturally they developed their own units. So there was a variety of units that was available to try and measure energy also, like many other things, naturally. So there was the British system, the MKS system, and the SI system, and so on. Let's not go into details of all that right now. Um, but some of the words we have heard, we hear of what is known as joule or kilojoules or kilocalories or erg. And if you look at all your food packets, it will be written so many kilocalories or so many kilojoules will be released by 1 gram. And then people from engineering and other areas have heard of units like BTU, British Thermal Unit, depending upon how much of coal that you burn. And they nowadays talk of the coal equivalent or the oil equivalent or 1 meter cube of a particular gas that is being burnt to release a certain amount of energy. All these are all units that are being used everywhere around. The heat units are different from the mechanical units. And the mechanical units and the electrical units and the sound units are all very much similar. So there has to be some way in which we know what all these units are. I just can't say one calorie is same as 1 joule, or it is equal to one electrical unit that I talked of for electricity that we get at home. There has to be a certain conversion factor, and that is something that we must know of. To understand this, let's look at another concept. Uh, Currency, money, for example. Um, I have dollars, so I give somebody $100 and he returns me 100 rupees or 100 yen. Am I going to accept? Of course not. Because today the conversion rate between a rupee and a dollar is $1 is 83 rupees. What am I talking of? Why not $1 and 1 rupee being exchanged between me and my daughter? That's not going to work because the unit of currency has its own purchasing power. So it means that using a dollar, I can buy a certain amount of sugar, and using a rupee, I can buy a certain amount of sugar. But when I use 1 rupee and when I use $1, the amount of sugar that I get is not going to be the same. So the purchasing power is different. So for $1, the amount of sugar I get will be 83 times more than the amount of sugar that I get for 1 rupee. So the conversion factor here between the rupee and the dollar is 83. In the same way, when I talk of heat units, which are in kilocalories, and when I talk of joule or kilojoule as the unit in terms of mechanical form or electrical form, it's not 1 joule equal to 1 kilocalorie. 4.2 joule will make 1 calorie. And when I talk of that uh, electrical unit that we use at home for electricity, that is known as kilowatt hour. That means I use 1 kilowatt of power for 1 hour. And that boils down to 3600 or rather 360000 so many joule. So there is a conversion factor at every stage. So whenever we talk of energy, it's not just to say that I have so much amount of electrical energy and I convert it directly into heat energy. It doesn't work that way. There is one more aspect related to this, and that is, how do we use this? Olden days it was fine, but today when I talk of using energy in such forms, um, I, for example, want to go from A to B. I go by a train or by a car or by some vehicle which has an electrical engine, uh, petrol engine. And so what I do is put petrol there and burn the petrol, get mechanical movement out of it and reach my destination. But the trouble is, when I put petrol worth X amount of energy, what I get out of it is Y amount of mechanical work, which is always less than X. The reason is quite a bit of it is lost in the heat produced by the engine. That's not going to drive me ahead. And there could be a lot of sound produced by the engine, so that's also a waste. And there could be wear and tear, that's also a waste. So, what I get out of a certain amount of fuel and what I put in, it is found that what you put in is far more than what you get out of it. And this is expressed in terms of the amount of efficiency of the system. So whenever I talk of conservation of energy, that I put heat energy and what I get is electrical energy. No, there are some parts which are lost to the surroundings. And I'm not really interested in the electrical energy. I'm interested in how the electrical energy is being used. So naturally in the process, there is a lot of loss. And this is talked of in terms of the efficiency of the system. So whenever we talk of energy, we know that it is conserved. We know that the universe has a vast amount of energy, but we need to preserve it and we need to use it more efficiently. Like what happened in case of bulbs, and now we have the diodes which are far better than the other ones. So these are some of the basic ideas of the type of energies that we have and the basic concepts related to their conservation and units. I'll go into details of each of these individually later on. as we proceed in our variety of talks in science. If you've liked whatever I have said, please tell your friends about it. Please like and subscribe to this channel. And till we meet again for science also sometime, probably alternate weeks. Namaskar.